For this video, we are going to be discussing some of the patterns and relationships that we see amongst the equations with even exponents, as well as looking at some of the equations with odd exponents and seeing what their patterns and relationships are as well. So if you remember from the last video, we just kind of scratched the surface on what was going on here. We concluded that the equations seem to approach these vertices, but we weren't sure if they actually ever touch them. And when we see these like different patterns in the way that all these equations are interacting, we notice that the even equations are kind of making these closed figures, whereas the odd equations are making more of these curves that approach this upper corner here. So playing around a little bit with the even equations, we see that the larger the exponent, the closer and closer that it gets to actually reaching the square shape. But unfortunately, it actually never does reach those vertices. But why does this happen? After trying to make sense of this for a while, I decided to really shift my focus to more of the zero exponent and see if that would help some of my thinking. I was met with surprising results when I entered in this equation, as nothing appears on the graph. I then began to think of, why would this happen? Why would nothing show up? And I remembered that there is no exponent in which the sum of two arbitrary numbers, both raised to the power of 0, will equal 1. This happens because any number to the power of 0 is equal to 1. This thought immediately spurred into action some understanding about why the square could not be created. In the equation x to the b plus y to the b equals 1, for some positive integer b, we know that 1 can never be entered for x or for y because there exists no exponent in which those two are going to combine and equal 1. So we also know that in this certain equation, we have it set to where we're only looking at even numbers because those are going to give us our closed shapes. So when you raise a number to an even exponent, we know that whether the number is positive or negative, it's going to produce a positive number. So when we think about 1, -1, -1, 1, and -1, -1, we know that, again, we're never going to be able to plug those numbers in here and get 1 as our solution. So this explains why the square is never created, because those points that I just mentioned can never be attained. We can use this thinking to further our understanding of why the odds also behave the way that they do. So looking at our exponents that are odd, we see that they create these curves, as mentioned earlier, that approach kind of this point here, this 1, 1. All right, well, when we look at the exponent of 1 here, we see that the line y equals 1 minus x is produced. Inputting the points that we looked at earlier, we also see that they, quote unquote, break the equation. The graphs can approach this 1, 1, or as it could look as the corner of the square, but they're never actually going to touch this point for the same exact reason as to why the square was never able to be completed. When I was discussing this problem further with my classmate Tyler Hamilton, he brought up an intriguing notion that I had not considered before. So when you think about the definition of even numbers, you know that there exists a number such that it equals 2 to the n, meaning that the number is divisible by 2, basically. So we can take that information and apply it to our equations and see that this can actually be written as x to the 2n plus y to the 2n equals 1. And further, we can even rewrite this as x squared to the n plus y squared to the n equals 1 because of our laws of exponents. So if you notice, this x squared plus y squared equals 1 was our original equation for the circle. So basically this shows us that the equations with even exponents are just taking this equation of the circle and raising it to a power of n. Similarly, we can think about odd functions in the same way, just rewriting their equations using the definition of odd functions. So when we look at any equation with an odd exponent, we know that we can rewrite it as x to the 2n plus 1 plus y to the 2n plus 1 equals 1 for any number n. And so this can actually further be rewritten as x to the 2n x plus y to the 2n y equals 1 for any integer n. So what this means for the odd equations is that it is basically taking this equation here and multiplying in another x and another y in order for us to get these curves that we see. I don't think that this really helps us prove anything about why the shapes never really reach those points, because we kind of already proved that, but I thought this was just a really cool way to look at our different equations.